autumn to winter, winter into spring, spring into summer, summer into fall. So rolls the changing year, and so we change. Motion so swift, we know not that we move. The changes in seasons have inspired a lot of poets. But scientifically speaking, do you know how the phenomenon of changes in the seasons can be explained? It's all connected to planetary motion. Ptolemy showed the world a geocentric solar system, which was centered on the Earth, with the Moon, the Sun, and 5 planets revolving around the Earth in perfect circular orbits. Then came Nicolaus Copernicus, who presented a heliocentric solar system. This model showed the Sun at the center of the solar system, with planets revolving around the Sun in circular orbits. However, neither of these models could explain the variations in seasons or the lengths of days over the year. Finally, Johannes Kepler, a German mathematician, astronomer, and astrologer, in his laws of planetary motion, explained that planets revolve around the Sun in elliptical orbits, resulting in the change in distance from the Sun at various times of the year. Kepler's laws helped explain, among other things, the reason for changing seasons on Earth. In this lesson, you will learn about Kepler's laws of planetary motion. At the end of this lesson, you will be able to list Kepler's laws of planetary motion, explain the law of orbits, explain the law of areas, and explain the law of periods. In the early 16th century, Kepler studied the shortcomings of Copernican model using the data gathered by his teacher, Tycho Brahe. Kepler concluded that all the planets revolve around the Sun in orbits, which were elongated rather than perfect circles. Based on his observations, Kepler propounded 3 laws of planetary motion, known as Kepler's laws. Kepler's 3 laws of planetary motion are the law of orbits, the law of areas, and the law of periods. Let's look at each law one by one. Kepler's first law, the law of orbits, states that the orbit of a planet is an ellipse with the Sun at one of the foci. An ellipse is a closed, curved shape that is defined by 2 points, called foci, representing an elongated circle. The sum of the distance from a given point on the ellipse to the foci is always constant. In the given figure, a plus b is always constant. As you can see, in an elliptical orbit, the distance of the planets from the Sun is not constant. The closest point on a planet's orbit from the Sun is called perihelion, and the furthest point from the Sun is called the aphelion. When a planet like Earth is far from the Sun, the amount of heat reaching the Earth from the Sun is relatively less. Hence, we experience a cold season. Conversely, when Earth is nearer the Sun, we experience a hot season because more heat reaches the Earth. Kepler's second law of planetary motion, also known as the law of areas, states that the line joining the planet to the Sun sweeps out equal areas in equal intervals of time as the planet travels in its orbit. Let's explain this through an example of Earth's movements. Suppose the Earth takes 1 month, that is 30 days, to travel from point P to Q on its orbit. Imaginary lines drawn from the Sun to points P and Q, together with the Earth's orbit, enclose a roughly triangular area. This area is equal to the area covered for any 30-day duration during the year, regardless of the Earth's position in its orbit. Thus, as shown, area A1 equals area A2. Further, according to Kepler, the speeds of planets in their orbits vary through the revolution around the Sun. When planets get closer to the Sun, they move faster. Conversely, as they get further from the Sun, they move with relatively lower speeds. Therefore, the speed of a planet is highest at perihelion and slowest at aphelion. Kepler's third law, the law of periods, defines the relationship between the orbital period of a planet and the average radius of its orbit. The orbital period of a planet, denoted by T, is the time taken by the planet to make a complete revolution around the Sun along its orbit. The average radius of the orbit of a planet is also the mean distance of the planet from the Sun. For example, suppose R1, R2, and so on are the distances of Earth from the Sun for n number of positions of Earth in its orbit. Then, the average radius of Earth's orbit can be calculated as shown. The law of periods states that the square of orbital period T of a planet is proportional to the cube of its mean distance r from the Sun. Hence, you can express the law of periods as T square proportional to r cube, where T is the orbital period of the planet in Earth years, and r is the mean distance in astronomical units. Astronomical unit AU is the mean distance between the Earth and the Sun. Thus, an astronomical unit is approximately 93 million miles or 150 million kilometers. If we consider 2 planets, A and B, and compare their mean distances from the Sun and orbital periods, we get the relationship as TA square divided by TB square is equal to RA cube divided by RB cube, where TA is equal to orbital period of planet A. TB is equal to orbital period of planet B. RA is equal to mean distance of planet A from the Sun, and RB is equal to mean distance of planet B from the Sun. Scientists use Kepler's laws to determine the positions and the orbital periods of various planets in the solar system. These laws also help us in calculations involved in determining orbital periods of satellites, natural as well as artificial. This brings us to the end of this lesson on Kepler's laws of planetary motion. In this lesson, you learned about Kepler's 3 laws of planetary motion. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson. Oops! Now, is that ball coming back or not? Looks funny, doesn't it? But that's the way things could be if there was no gravitational force to hold things to the Earth's surface. In this lesson, you will learn about the universal law of gravitation, gravitational force, and its effect on a freely falling body. At the end of this lesson, you will be able to explain gravitation, state the universal law of gravitation and explain its significance, derive the expression for gravitational force between the Earth and an object on the Earth's surface, calculate the acceleration due to the gravity on Earth, differentiate between mass and weight, and compare the weight of an object on the Moon with its weight on Earth. When an apple fell on Newton's head, he figured out that the Earth exerts a force of attraction on all bodies near its surface. The force of attraction exerted by the Earth on any other body is called gravity. Gravity is what brings things down again when we throw them up. Like Earth, all bodies in the universe attract each other. The force with which all bodies in the universe attract each other is called gravitational force. The revolution of the Moon around the Earth is also a result of gravitational force, which acts towards the center of the Earth. Such a force exerted on a body moving in a circular path that acts towards the center of the circular path is known as centripetal force. Newton originally thought that like an apple or a ball, all objects should fall to Earth. However, based on his study of centripetal forces, he was able to explain why this does not happen. When a body A is in circular motion around another body B, it experiences a force directed away from the center of the circular path, which is equal in magnitude and opposite in direction to the centripetal force. This prevents the two bodies from moving towards each other due to gravitational force of attraction between them. This is the reason that the Moon and the planets revolve in their respective orbits instead of falling on each other. For a better understanding of centripetal force, let's observe a game of hammer throw, an Olympic athletic event. Each thrower swings a hammer around and releases it at a point such that the hammer flies off in one direction. You can observe that the hammer gradually gains velocity as the thrower swings it around, and the hammer flies off in a straight line which is tangent to the circular path of its revolution. While the athlete is swinging the hammer, that is, the hammer is in revolution, its direction of motion and hence its velocity changes continuously. This change in velocity produces acceleration on the hammer. This acceleration is directed towards the center of its circular path. Acceleration directed towards the center results in a force directed towards the center. This force is called the centripetal force, which means a center-seeking force. The reason for the motion of the Moon around the Earth is similar to that of the motion of the hammer, just discussed. The gravitational force of attraction between the Earth and the Moon provides a centripetal force for the Moon. In the absence of centripetal force, the Moon would follow a tangential path similar to that observed in the case of the hammer discussed. In that case, our Moon would have flown away from the Earth long back. Consider the force that holds things to Earth, the occurrence of tides due to the motion of the Moon and the Sun, the revolution of the Moon around the Earth, and the motion of planets around the Sun. What do you think is common among all these phenomena? Nothing, you may say. However, through the universal law of gravitation, Newton explained the relationship between several such phenomena that were earlier thought to be unrelated. Newton's universal law of gravitation states that every object in the universe attracts every other object with a gravitational force, which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The gravitational force acts along the line joining the centers of the two bodies. The law is universal since it is applicable to all objects, regardless of their masses or their positions in the universe. To derive the expression for the universal law of gravitation, consider two spherical bodies. Let m1 be the mass of the first body, m2 be the mass of the second body, r be the distance between the centers of the two bodies, which is generally referred to as the distance between the bodies. F be the force of attraction between the two bodies. According to Newton's universal law of gravitation, gravitational force between two bodies, F, is directly proportional to the product of masses of both the bodies, m1 and m2, and inversely proportional to the square of the distance between them, r. By combining both these relationships, we get the gravitational force between the bodies as F proportional to m1 m2 divided by r square. To equate this relationship, we use a constant of proportionality, g, which is the universal gravitational constant. This gives us F is equal to g m1 m2 divided by r square. If m1 and m2 each equals 1 kilogram and r equals 1 meter, you get F is equal to g. Thus, the universal gravitational constant is numerically equal to the gravitational force between two bodies, each possessing a unit mass, separated by a unit distance. The SI unit of the universal gravitational constant is Newton meter square per kilogram square. Henry Cavendish found the value of G with the help of a sensitive balance. G equals 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. In deriving the expression for the gravitational force of attraction between two bodies, Newton used Kepler's third law of planetary motion. This helped him conclude the second part of the relationship known as Newton's inverse square rule. This rule states that the gravitational force F between two bodies is inversely proportional to the square of the distance between them. In deriving the inverse square law, Newton assumed that the planetary orbits are circular. If a planet revolves around the Sun in a circular orbit of radius r with a velocity v, also referred to as the orbital velocity of the planet, then the force on the planet is F proportional to v square divided by r. Let's call this equation 1. The orbital velocity of the planet v is equal to 2 pi r divided by t, where t is the orbital period of the planet. Squaring both the sides and simplifying, we get equation 2. V square is equal to 4 pi square r cube divided by rt square. Substituting equation 2 in equation 1 and simplifying, we get equation 3. In equation 3, 4 pi square is a constant. According to Kepler's third law, r cube divided by t square is also constant. Therefore, we can eliminate these constants from the relationship. Eliminating the constants, we get the relationship as F proportional to 1 divided by r square. Newton extrapolated these findings to all the bodies in the universe. Therefore, the gravitational force F is inversely proportional to the square of the distance between the two bodies. As we mentioned before, when you throw an object up, it comes down due to gravity. Thus, when an object such as this boulder is pushed or thrown from a height, it falls to the earth. Such an object is said to be in free fall. An object is in free fall when it falls to the earth under the sole influence of gravity. A fruit falling off a tree or a sandbag thrown off a hot air balloon hurtle towards the earth in a free fall. However, a parachutist descending from an aircraft is not in free fall, since he uses the parachute to counter the gravitational force of Earth. A freely falling body is always under the influence of the gravitational field of the Earth. But not all the bodies under the influence of the gravitational field of the Earth are freely falling bodies. A body under the influence of Earth's gravitational field can be a body dropped from a certain height, like a ripe fruit falling off a tree. A body projected vertically downward from a certain height with some velocity, such as a ball thrown down by a boy from the 5th floor of a building. Or a body projected vertically upward, for example, a stone thrown vertically upwards. Objects in free fall move only in one direction. However, their velocity changes as they fall. A change in velocity results in acceleration. The acceleration of a freely falling body due to the gravitational force of the Earth is known as acceleration due to gravity. Acceleration due to gravity is denoted by the small letter g and is measured in meter per second square. How can you determine how long it will take an object in free fall to reach the Earth from a specific height? To perform such calculations, you need to know the value of acceleration due to gravity. So, let us now derive the expression for acceleration due to gravity g. Consider a freely falling object of mass m. Let the capital letter M denote the mass of Earth. D be the distance between the free-falling object and the center of the Earth. And R be the radius of Earth. Since the object is in free fall, the gravitational force F on the object is the product of its mass m and acceleration due to gravity g. Let's call this equation 1. The gravitational force F between the Earth and the free-falling body can also be calculated using Newton's universal law of gravitation. F is equal to G into m divided by d square. When the object is near to or on the surface of the earth, the distance d is taken as equal to the radius of the earth r. Let this be equation 2. By equating 1 and 2, we can calculate the acceleration due to gravity as g is equal to g multiplied by m divided by r square. Since the earth is not a perfect sphere, its radius is maximum at the equator and minimum at the poles. Hence, the acceleration due to gravity is greater at the poles than at the equator. However, this difference is negligible for bodies on Earth. To calculate the value of acceleration due to gravity g, we need to substitute the values of universal gravitational constant g, mass of the Earth m, and radius of the Earth r in the expression we derived. On substituting and simplifying, we find that the value of g is approximately 9.8 meter per second square. Acceleration due to gravity at a place on Earth is the same for all bodies, irrespective of their masses. Let's use two identical objects with different masses to verify this statement. Drop a metallic ball and an identical wooden ball from a height. Do you notice that both reach the surface of the Earth simultaneously? Since the mass of the metallic ball is greater than that of the wooden ball, the force of gravity on the metallic ball is greater than that on the wooden ball. However, it doesn't seem to make the metallic ball fall faster than the wooden ball. This proves that acceleration due to gravity on Earth is the same for all bodies irrespective of their masses. In your study of motion, you have learned about the equations of motion. There are three equations of motion. 1. V is equal to u plus at. 2. S is equal to ut plus half at square. And 3. V square is equal to u square plus 2as. These equations relate displacement, velocity, and the acceleration of a body. The acceleration of all freely falling bodies is due to gravity. Therefore, we can simplify these equations for freely falling bodies. Now let us observe how these equations of motion are modified for freely falling bodies in all three cases. The first one is the case where a body drops from a certain height. Here, the initial velocity of the body u is 0. The acceleration of the body a is the acceleration due to gravity g. This value is positive because the velocity of the body increases as the body descends. Let's consider how the three equations change in this situation. Our first equation is v is equal to gt, where v is the velocity of the dropped body at the end of t seconds. Similarly, the second equation becomes h is equal to half gt square, where h is the distance covered by the dropped body at the end of t seconds. The third equation becomes v square is equal to 2gh, where v is the velocity attained by the dropped body at the moment it covers distance h. In the second case, we consider a body projected vertically downward with some initial velocity. In this case, the initial velocity of the body is not 0. The acceleration a is again the acceleration due to gravity g. By substituting a is equal to g in the three equations, we get the revised equations as shown. Acceleration due to gravity is positive in this case as well as the velocity of the body increases downwards. However, in the third case, the body is projected vertically upward. In such a scenario, the velocity of the body decreases as the body ascends. Therefore, the acceleration of the body becomes negative. By substituting A is equal to minus g in the three equations, we get the revised equations as shown. How much do you weigh? 60 kilograms? 80 kilograms? What we popularly refer to weight is actually mass. So, what's the difference? How can you gauge your real weight? Mass is the amount of matter contained in a body, while weight is the force with which a body is pulled towards the center of the earth. Thus, weight is the product of mass and acceleration due to gravity, that is, W is equal to mg. The value of g is approximately 10 meters per second square. Thus, if your bathroom scales show a reading of 60, your weight is 60 multiplied by 10, that is 600 Newton. Mass is a scalar quantity, hence it can never be zero. However, weight is a vector that can be zero when the acceleration due to gravity is zero, for example in space. In the SI system, mass is quantified in kilogram, while the unit of weight is Newton. A physical balance is used to measure the mass of a body. Weight is generally measured using a spring balance. The mass of a body is universal, meaning it remains the same throughout the universe. The weight of a body varies from place to place depending upon the gravitational force on the body at that place. This means that your mass on the Earth and on the Moon would be the same, but your weight would differ, because the acceleration due to gravity on the Moon is different from that on Earth. The gravitational force of the Moon is far less than that of the Earth. That's why, before cosmonauts fly on a mission to the Moon, they are acclimatized in a simulated lunar environment. This is to ensure that when they land on the Moon, they are able to move around easily even though the gravity is reduced. Because of this difference in gravity, the weight of a cosmonaut on the Moon differs from his weight on Earth. Let's find out how much this difference is. The mass of the Moon is 7.35 into 10 raised to the power 22 kilograms, and its radius is 1.74 into 10 raised to the power 6 meters. The mass of Earth is 5.97 into 10 raised to the power 24 kilograms, and its radius is 6.37 into 10 raised to the power 6 meters. Using the universal law of gravitation, we can find the force or weight of an object of mass m on Earth and the Moon. By substituting the values and solving, we get the weight of the object on the Moon as 2.43 into 10 raised to the power 10 into g into m. Similarly, we get the weight of the object on Earth as 1.47 into 10 raised to the power 11 into g into m. By comparing these results, we can determine the relationship between the weight of an object on the Earth and the Moon. Thus, the weight of an object on the Moon would be approximately 1/6 of its weight on Earth. For example, if the cosmonaut weighs 600 Newton on Earth, he would weigh approximately 100 Newton when he lands on the Moon. This brings us to the end of this lesson on the universal law of gravitation. In this lesson, you have learned about gravitational force, universal law of gravitation, free fall, and acceleration due to gravity. The following section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson. A truck with thin tires looks odd, doesn't it? It doesn't look like it can manage the load it's carrying. As we've all seen, trucks need wide tires. On the other hand, let's look at a housewife trying to chop vegetables with a thick, blunt knife. She's not having much success. To chop efficiently, she needs a knife with a sharp blade. What is the significance of the width of the tires and the sharpness of the knife in these cases? This can be explained through the concept of thrust and pressure. The truck needs wide tires to reduce the pressure of the cargo. The knife needs a sharp blade to increase the pressure exerted on the vegetables. In this lesson, you will learn about thrust and pressure, with special emphasis on thrust and pressure in liquids. At the end of this lesson, you will be able to define thrust and pressure, differentiate between thrust and pressure, calculate thrust and pressure in given situations, explain the effect of pressure exerted by fluids, derive the expression for calculating pressure in fluids, state Pascal's law, and explain the applications of Pascal's law. Thrust is a vector force acting normally on a surface and is denoted by F. For example, consider the simple act of driving a nail into a wall with a hammer. The force that you exert on the hammer during this activity is thrust. Thrust is measured in dyne in the CGS system, and Newton denoted by N in the SI system. We have seen that nails have pointed tips to help us drive them into surfaces. Why is it important for a nail to have a pointed tip? For that matter, why is it important to have a sharp knife to chop vegetables? The force you apply in driving a nail or chopping vegetables is translated into pressure, depending upon the surface area of the object on which the force is applied. In other words, pressure is the amount of thrust acting on a unit area. Pressure is denoted by the letter P. Hence, pressure is calculated by dividing thrust with area. The lesser the surface area of an object, the more the pressure applied by that object. The pointed tip of the nail minimizes the surface area of the nail on which thrust is applied. Therefore, while driving the nail into the wall, the pressure of the hammer is maximized, which helps drive the nail into the wall. Pressure is scalar and is measured in dyne per centimeter square in the CGS system, or Newton per meter square or Pascal, denoted by PA in the SI system. Another example will help illustrate further the distinction between thrust and pressure exerted by a body. Take a piece of foam and two identical metal blocks, say A and B, weighing 300 grams. The length, breadth, and thickness of these blocks are 30, 20, and 10 centimeters respectively. Place the metal block A vertically on the foam and the other iron block B horizontally. Now let's compare the compression of the foam where blocks A and B are placed. The foam shows more compression where the metal block A is positioned vertically. Considering that both the blocks have the same length, breadth, height, and weight, why do you think we see this difference in the compression of foam? This difference can be attributed to the difference in pressure exerted by each block. Block A was placed vertically over the sheet of foam, while block B was placed horizontally. The surface area of block A in touch with the foam is 200 square centimeters. On the other hand, the surface area of block B in touch with the foam is 600 square centimeters. Using the formula for pressure, we can now calculate the pressure of blocks A and B on the foam. The pressure of block A on the foam is 1,500 dyne per centimeter square. The pressure of block B on the foam is 500 dyne per centimeter square. Thus, in block A, the same thrust was acting on a smaller surface area. Hence, the pressure exerted by block A was higher. This explains why the foam showed more compression where block A was placed. The thrust exerted by a body remains constant, placed in any position. However, the pressure exerted by the body changes with a change in positions. Let's look at another everyday example. You may have used chairs in which the seat is created from plastic wave. These chairs are quite safe to sit on. However, if you try standing on such a chair, the plastic wire may give way under the strain. This is because when you stand on the chair, the area of contact becomes much smaller, and the pressure on the wire crosses the safety limit. In both the cases, the weight of the man, that is the downward force acting on the chair, is the same. However, the area on which it is acting has changed, leading to change in pressure exerted on the seat of the chair. So far, we looked at examples of thrust and pressure in solids. However, thrust and pressure are equally applicable to the other states of matter, liquids and gases. Liquids and gases are collectively referred to as fluids. Since all fluids have the tendency to flow, like solids, fluids also have weight, and this weight exerts a force on the walls and base of a container. We can demonstrate the effect of pressure in liquids through a simple example using a plastic bottle. Fill the plastic bottle completely with water. Then make a small hole in the lower half of the wall of the bottle. You will see that the water gushes out through the hole with considerable force. This force is due to the pressure of the fluid at that point. So, how do we calculate pressure in fluids? To derive an expression for pressure in fluids, let's consider a beaker filled with a fluid, say water, of density D to a height h. Drop a coin with the area of cross-section A into the beaker. The volume of the water column above the coin V is equal to area of cross-section of the coin multiplied by the height of the water column. This gives us equation 1. Volume V is equal to A multiplied by H. The mass of the water in column M is the product of the volume of the water and its density. Thus, M is equal to V multiplied by D. Substituting equation 1 in the expression for mass, you get equation 2. That is, M is equal to product of A, H and D. As you know, weight of a substance is a product of its mass and the acceleration due to gravity, g. Therefore, weight of the water column, W, is equal to the mass of the water column multiplied by g. Thus, W is equal to M multiplied by g. Substituting equation 2 here, you get equation 3. Weight of the water column acts normally on the object. Thus, the pressure P acting on the coin is the ratio of weight of the water column to the area of the coin. That is, P is equal to W divided by A. From equation 3, we know W is equal to product of A, H, D and G. This gives the expression of fluid pressure P. P is equal to HdG, where H is equal to height of the water column, D is equal to density of the water, and G is equal to acceleration due to gravity. Using this expression, you can calculate the pressure applied by a fluid in the walls as well as the base of a container. The pressure at a point in a fluid is equal in magnitude in all the directions. Now let's look at some applications of the concept of pressure in our everyday life. You may have seen a warning at the back of trucks moving on highways. Caution: air brakes maintain 50 feet distance. So, air is used in applying brakes for these huge vehicles? Amazing, isn't it? In fact, the hydraulic brake system used in cars also involves usage of a fluid brake oil. Both these applications, air brakes and hydraulic brakes, are based on a law related to pressure. This law is called Pascal's law. Pascal's law states that a change in the pressure of an enclosed incompressible fluid is conveyed undiminished to every part of the fluid and to the surfaces of its container. Let's conduct an experiment to verify Pascal's law. We take a container with two openings of unequal cross-sectional areas. We fill this container with water and then close the openings with airtight pistons, 1 and 2. Then we push piston 1 inwards. As piston 1 is pushed inwards, piston 2 moves outwards. Thus, the increase in pressure through piston 1 is conveyed undiminished through the liquid to piston 2. As the area of cross-section of piston 2 is greater than that of piston 1, the thrust exerted on piston 2 is greater than that on piston 1. Hydraulic brakes as well as air brakes operate on the same principle. Let's see how this principle is applied in the construction of hydraulic brakes. A hydraulic brake system consists of a brake pedal, a piston, a master cylinder, 4 hydraulic lines, 4 brake cylinders, 8 brake pistons, 4 wheels, 4 restoring springs, Now let's see how hydraulic brakes work. The master cylinder and the brake cylinder are connected to a thick copper pipe called the hydraulic line. Thick brake oil is filled in the master cylinder and the brake cylinders, and they are fitted with airtight pistons. The master cylinder is connected to the brake pedal. A brake cylinder is connected to the metallic rim of each of the wheels. Now let's see how this arrangement of hydraulic brakes works to enable a driver to stop a car when driving. When the brake pedal is pressed, the piston in the master cylinder goes in forcing brake oil out with some pressure into each of the brake cylinders. At each brake cylinder, two opposed pistons attached to brake shoes are forced outwards. The outward movement of brake shoes presses the brake bands against the inner surfaces of the wheels to stop their rotation. When the brake pedal is released, the restoring springs at each wheel restore the pistons to their original positions. Thus, hydraulic brakes in automobiles employ the concept of pressure to enable drivers to stop heavy vehicles by applying a relatively light touch on the brakes. This brings us to the end of the lesson on thrust and pressure. In this lesson, you learned about the concept of thrust and pressure, the expression to calculate pressure in a liquid, and applications of thrust and pressure. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard.
So we are going swimming?
Yes. Let's wait for the pool to get free.
Ouch!
Haha! Did you know that Archimedes, a Greek scientist, went through a similar experience? While most of us have heard the story where Archimedes ran through the streets yelling, "Eureka!" the real problem he was struggling with at that time is not so well known. According to a famous Roman writer, a new crown had been made for King 𝙁𝙗𝙃, and Archimedes had to determine whether it was of pure gold. The king wanted reassurance that no silver had been added to the crown by a dishonest goldsmith. To do this, Archimedes needed to find a method to determine the volume of an object with an irregular shape. In this lesson, you will learn how Archimedes solved this problem and propounded the Archimedes principle. You will also learn about buoyancy and flotation of objects. At the end of this lesson, you will be able to explain Archimedes' principle and its applications, to find relative density, explain the applications of relative density, apply the formula of relative density to calculate the density of a given substance, define buoyancy, and explain the phenomenon of flotation and sinking using the concept of buoyancy.
So, how did Archimedes solve the problem? And what did water have to do with it?
While taking a bath, Archimedes noticed that the level of water in his tub rose as he got in. He realized that he could use this effect to determine the volume of the king's crown. The submerged crown would displace an amount of water equal to its own volume. Based on this, he eventually propounded the Archimedes principle. This principle states that when a body is immersed completely or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. We can verify Archimedes' principle through an experiment. From a spring balance, suspend a small block of iron weighing W1, say 700 grams. Take an overflow jar and fill it with water until it is on the verge of overflowing. Under the spout of the overflow jar, place an empty beaker that weighs W2, say 150 grams. Gently lower the iron block suspended from the spring balance into the overflow jar, till the block is completely immersed in water. The water overflows into the empty beaker placed under the spout of the overflow jar. Now, note the weight of the iron block in water as well as the beaker with the displaced water. The weight of the iron block in water, say W3, is 600 grams. The weight of the beaker, say W4, is 250 grams. Thus, there is an apparent loss in the weight of the iron block. The apparent loss of weight of the block is equal to W1 minus W3. This is equal to 100 grams. The weight of the water displaced is equal to W4 minus W2. This equals 100 grams. You can see that W1 minus W3 is equal to W4 minus W2. Thus, this verifies that the difference of weight of the iron block inside and outside the water is equal to the weight of water displaced into the beaker.
So, once Archimedes had determined the volume of the crown, he could find out whether or not it was made of pure gold.
That's right. Remember, mass of an object is a product of density and volume. So, knowing the density of gold and the volume of the crown, Archimedes could perform the necessary calculations to solve the problem. The Archimedes principle finds many applications in our lives. One of these applications is determining the density of a given liquid using an instrument called a hydrometer. A hydrometer is generally made of glass. It consists of a cylindrical stem and a bulb. The bulb contains a mercury or lead shot to make it heavy. This ensures that the hydrometer floats upright in a liquid. To determine the density of a liquid, it is poured into a tall jar, and a hydrometer is lowered gently into the jar to float freely on the liquid. The hydrometer reading gives the density of the liquid. For example, if we place the hydrometer in a jar of carbon tetrachloride, the hydrometer shows a reading of 1.6. Thus, the density of carbon tetrachloride is 1.6 gram per centimeter cube. As you know, the density of a substance is the mass of a unit volume of that substance. The density of a given substance under specified conditions remains the same and is one of its characteristic properties. However, sometimes it is more convenient to use another measure called relative density. The relative density of a substance is typically referred to as the ratio of density of the substance to the density of water. It indicates how heavy or light that substance is when compared to water. For laypersons, the concept of relative density may be easier to understand than density. For example, if we state the density of iridium as 22,650 kg per meter cube, not everyone may easily grasp how heavy iridium really is. However, if we say iridium is over 22 times as dense as water, the number gives us a realistic idea of weight of the unit volume of iridium. As a more common example, the relative density of silver is 10.5. This means silver is 10.5 times as heavy as water. Since the relative density is a ratio of similar quantities, it has no unit. However, while calculating the relative density of a substance, care should be taken that densities of the substance and water are expressed in the same system of units. The concept of relative density finds many applications, especially calculation of the densities of given liquids. For example, a lactometer is used to test the purity of milk on the basis of its relative density. An alcohol meter uses the concept of relative density to determine the alcoholic strength of a liquid. Similarly, a saccharometer is used in determining the amount of sugar in a solution. The formula for relative density of a given substance is: relative density is equal to density of a substance divided by density of water. Given the relative density of a substance, you can use this formula to determine the density of that substance. For example, the relative density of carbon tetrachloride is 1.6. To calculate its density, let's substitute the given values in the formula. Relative density of carbon tetrachloride is equal to density of carbon tetrachloride divided by density of water. 1.6 is equal to density of carbon tetrachloride divided by 1 gram per cubic centimeter. Density of carbon tetrachloride is equal to 1.6 into 1 gram per cubic centimeter. Therefore, the density of carbon tetrachloride in CGS system is equal to 1.6 gram per cubic centimeter. Now let's look at another aspect of Archimedes' principle, which explains the concept of floating and sinking, also known as buoyancy. As Archimedes' principle mentions, when a body is immersed completely or partially in a fluid, it experiences an upward force. The upward force exerted by a fluid on any object is called upthrust, the buoyant force, or simply buoyancy. The concept of buoyancy explains why certain objects float on water while others sink. All objects experience buoyant force when immersed in water. Floating and sinking of objects depends on how the density of the object compares with the density of water. An experiment will help illustrate this concept. First, we take a beaker filled with water. Find 2 identical coins, one of metal and the other of plastic. Place both the coins on the surface of the water. The density of water is 1 gram per cubic centimeter. The density of iron is 7 gram per cubic centimeter. The density of plastic is 0.8 gram per cubic centimeter. The plastic coin floats and the metal coin sinks.
So how can we determine whether the buoyant force on an object will exceed its weight?
The magnitude of this buoyant force depends on the density of the fluid. Therefore, the floating and sinking of objects depends on how the density of the object compares with the density of water. The plastic coin floats in water because the density of the plastic coin is less than the density of water. Therefore, the upthrust of water on the plastic coin is greater than the net weight of the coin. On the other hand, the iron coin sinks because the density of the iron coin is higher than the density of water. Therefore, the upthrust of water on the metal coin is not able to overcome the net weight of the coin. Thus, according to the principle of buoyancy, objects with a density less than that of a given liquid float on that liquid. Objects with a density greater than a given liquid sink when placed in that liquid.
That's cool. But wait a minute. The density of iron is greater than that of water. So how is it that if we drop a piece of iron in water, it sinks? But our ships are built of iron and steel parts. and they don't seem to have any problem staying afloat in water.
That's a good question. To better understand why a ship floats, let's look at a very simple everyday example of buoyancy. Take an empty glass bottle and close its cap airtight. Put the bottle in a bucket filled with water. Then try to immerse the bottle in water. You'll observe that attempts to push the bottle down in the bucket are unsuccessful, and the bottle floats on water, even though the density of glass is higher than that of water. Here's the reason why. The bottle contains air inside it. The volume of the bottle includes the volume of air in it. The density of air is much less than that of water. This means that the overall density of the bottle becomes lower than that of water. Hence, the upthrust on the bottle is greater than the weight of the bottle. Due to this, the empty airtight bottle is pushed upward when we try to immerse it completely in water. Therefore, the glass bottle floats on water. In order to make the bottle immerse completely in water, the volume of water equivalent to that of the bottle must be displaced. Note, to keep the bottle completely immersed, the upward force on the bottle due to water must be balanced. This can be achieved by an externally applied force acting downwards. This force must at least be equal to the difference between the upward force and the weight of the bottle. The reason for flotation of the ship is similar to that of the flotation of the glass bottle. Even though the density of iron is more than that of water, the ship does not sink. The total volume of the ship includes the volume of the air in it and the volume of the metal. This reduces the overall density of the ship to a value much less than the density of water. Hence, the ship does not sink.